All right, we are going to talk today about implicit differentiation and related rates. So I want to do a couple of examples of implicit differentiation, and then I want to do two examples of the related rates because those are the word problems and those can be a little bit tricky. But I hope you already read the sections. So remember what we're doing implicitly is we're deriving with respect to another variable. So I just want to do some examples. So one example here, let's find, this is kind of the first example that they gave you at the beginning of the book, and this is a great example of when implicit differentiation is very useful for us. So how about find the equation of the tangent line. My handwriting is a little, it's a little messy today. I apologize for that. So find the equation of the tangent line to the circle. Whoa. That should be one eye. Let's just keep this easy. X squared plus y squared equals 25 at the point 3. Well, let's get interesting here. How about at the point 3, -4? Okay, so the whole idea here is that, you know, if I were really to want to find this, if I look at a circle, this is good. If I look at the circle, this is a circle of radius 5, right? Oh, and my circle is not going to be great, but we'll just do that, rip the Band-Aid off. And where's that point 3, -4? So I would go over 3 and down -4. And I want the equation of the tangent line at this point right here. So for right now, the problem is, and you read this in the book, is if I wanted to find that, I would have to solve for y, right? So if I wanted to do this as is, I would need to solve for y. I would get 25 minus x squared. I would take the square root, and I would need a plus or minus. So depending on if y is positive or negative, that depends on which one we're going to take. In this case, y is negative because I want it at 3, -4, because the circle is not a function. And then if I were to do this, I would need to take y primed. I would have to do the general power rule, the chain rule, and it could get a little messy. So what implicit differentiation does for us is it allows us to take a function that is implicitly defined. So I shouldn't say function, excuse me, an equation that is implicitly defined. It allows me to take the derivative of this without having to actually explicitly solve for y. So as you saw, what I want to do is I want to derive with respect to x because I'm looking for the tangent line, right? And the tangent line, the derivative gives me the slope. That tells me how is my slope changing with respect to x, okay? So I take the derivative with respect to x of both sides. So the nice thing here is that x squared is already in terms of x. So how does x squared change with respect to x? Well, it would just be 2x. That would be the derivative that we know and love, which is 2x. Now, y squared, though, remember, we need to treat this as a function of x. And we know it is a function of x. Look at it. We solve for it up here. It's actually 2 functions of x. So when I take the derivative of this, I need to think of this as the general power rule. So the general power rule says, bring the 2 down, leave the inside, take 1 away, and then multiply by the derivative of the inside. But I don't know actually what y is. It's just a function of x. So I'm going to say the derivative of y. Well, it's just dy dx because I know it's all of this crap up here, but I don't actually want to write that all down. So I'm just going to put dy dx. Notice here, we actually technically did bring the 2 down, you know, do the general power rule. We multiply by the derivative of the inside, but that's just the derivative of x with respect to x, which would just be 1. So I technically have a 1 in there. And then this is all equal to 0 because 25 doesn't care what x and y are doing. It is a constant. It's not going to change with respect to x or y. So now what I need to do, remember to find the tangent line, right? I need my slope. And so to find the slope, I know that I need my slope, which is the derivative, evaluated at the point 3, -4. So, you know, I had an advisor in college, in graduate school when I was teaching calculus, that said to me, you know, Sarah, it's the calculus that's easy, it's the algebra that's hard. And that I think you're probably seeing that. That part right there wasn't too bad. Now what I need to do is I need to solve for dy dx. So I'm going to solve for dy dx. Okay, I'll just go ahead and show every step because I get that sometimes it's the algebra that's hard. So I just take this 2x and subtract it over. And now to get dy dx by itself, I'm going to divide both sides by 2y. So look at what this gives us. Implicit differentiation is pretty awesome. Because look at what we have now. Okay, we have dy dx equals a negative x over y. And what's even better about that is that that means if I want the slope of any tangent line on this circle, I just have to find the point that it goes through, and I just take the x value and I divide it by the y value, and I put a negative in front. So more specifically, what is the point that we care about? I want to evaluate dy dx at the point 3, negative 4. So what does that mean? Where I see an x, I'm going to put 3. Where I see a y, I'm going to put negative 4. So those will cancel, and we get 3/4. That's the slope of my tangent line. And if we look at this, I mean, that kind of makes sense to me because it looks like this slope is positive, right? So that makes sense that it would be positive. And then my last step, of course, would just be to write this as y minus a negative 4. So that'd be y plus 4 equals 3/4 times the quantity x minus 3. And that would be my final answer because that would be my tangent, the equation of my tangent line right there. So that's a really good example of why it's nice to have implicit differentiation. There are going to be other reasons why we need it here soon enough, but let's look at another example maybe that might be, I don't know, a little bit more interesting. For instance, let's find dy dx. Okay, and here's what I'm given. What I'm given is that I have this x squared plus 2xy plus y squared equals, let's say, 9. And I want to find dy dx. So this is not a function. That's when implicit differentiation is really useful, is when I have something that's not a function, like if it's a circle or a ellipse or something like that. The implicit still allows me to find equations of tangent lines even though I'm not dealing with a function. So again, first step, I'm going to take the derivative of both sides with respect to x. Okay? Because it's asking me to find dy dx. All right. So derivative of x squared with respect to x against that. Again, that is just 2x times the derivative of x with respect to x, which again is just 1. Now here, you got to be a little bit careful here because look at what we have. We have 2x, that is one function. And then I have this y, that is another function. So in your mind, you should be thinking, anytime you see two functions multiplied together, people, you must see that this is going to require the use of the product rule. You may not take the derivative of this and multiply it by the derivative of that. That is not correct mathematics. We saw that in the last section, well, 3.1. So what does the product rule say? It says leave the first times the derivative of the second, but what is the derivative of y with respect to x? Well, we'll just say that's dy dx because I don't know actually what y is, right? I know it's a function of x, but I'm not actually sure what it is. Then plus leave the second times the derivative of the first. So the derivative of 2x with respect to x is 2. Now I go on to y squared. This is going to be a chain rule or the general power rule. The derivative of the outside is 2y. The derivative of the inside is dy dx. And of course, 9 does not care what any of these things are doing. All right, so now what's our goal? Our goal is to solve for dy dx. So here's the algebraic trick. What you want to do in a situation like this, where I have two terms with dy dx, is I want to get everything that does not have a dy dx. So this guy does not have a dy dx, and this guy does not have dy dx. So I'm going to move those to the other side. So I'm left with 2x dy dx plus 2y dy dx. Okay, again, calculus is easy. It's the algebra that can be tricky. And I'm going to move these over. So this, I don't like y2. I'm going to make that 2y. I just subtract each one of these and I get a negative 2x minus 2y. Again, I just took these two terms, moved them over here. Now I'm going to factor out. This is kind of a cool one, actually, the way this worked. Factor out a dy dx. Okay. Now let's see. Let me make sure I didn't make a mistake there. Because this is going to be quite interesting, actually. So what we get here, the reason this is interesting is because I made it a plus instead of a minus up here. I had that in my notes that was a minus, but that's okay. So look at what we get. We get dy dx, so the thought process in all of this is going to be exactly the same. And I'm just going to divide everything by this 2x plus 2y. I can't remember now if I mentioned that we factor that dy dx out of each term. But look at what this is. If I take a negative 2 out of the top, I get x plus y. On the bottom, if I take out a 2, I also get x plus y. So this is why I was saying this one's kind of interesting. Because what we end up getting, I ran out of room, is we actually just get dy dx equals negative 1. That's kind of cool. And if you look at the graph of this, so why this works is this guy right here actually factors into x plus y, quantity squared equals 9. So if you square root that, we actually get two functions. We get x plus y equals 3, and we get x plus y equals negative 3. Well, if you solve both of these for y, you get negative x plus 3 is one of your lines, and y equals x, negative x minus 3. So what are the slopes of both of those lines? They're negative 1. And that's why we get the negative 1. But that process, that's what you're going to want to use for how to actually use implicit differentiation. I want to do two word problems and then we'll be done. Whoops. All right, so I just went ahead and type this out because I didn't want to take the time to write it with my tablet here. So, pause the video right now, write this in your notes, and then start with this. So here's what we have. We have, suppose a 26-foot ladder is placed against a wall. If the top of the ladder, so this is using related rates, by the way, to do application problems. And if you look on page 218, there is there's like a box at the very bottom of that page that gives you good steps on how to solve these word problems. And I would take the time to put those in your notes. So let's look at this one. I want to do this one for you. Suppose a 26-foot ladder is placed against a wall. So the idea here, so let me try and draw a picture for you. So here's my wall. This is a lovely wall. And I like to say that that we're living in perfect math world here, right? So all walls make perfect 90-degree angles with the completely flat ground. So this is my wall. I don't know, maybe it's a brick wall. So we'll do kind of a purple color. This is my wall. And what do I know? A 26-foot ladder is resting against the wall. So I need to make a ladder, okay? So here's my ladder. This is my ladder here. And I know that this ladder is 26. And I'm able to label that 26 because that does not change. So I just want to make sure you understand that. I can't always label it 26, but because that ladder's length does not change, I'm able to say that's 26. So look at what this is saying. If the top of the ladder is sliding down the wall at a rate of 2 feet per second, at what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet from the wall? So what is this talking about, right? Let's do what we did in the last section. Let's define some variables. I'm going to let x be the distance the bottom of the ladder is from the wall. I'm going to let y be the distance the top of the ladder is from the ground. So let's write down what we want and what is given. So what do I want and what is given? Okay, so let's look at that. So what is this asking? This is saying right here, if the top of the ladder is sliding down the wall at a rate of 2 feet per second, that is a given. The way we describe that is we say dy dt. Now, how do I know that that's dy dt? Because it says the top of the ladder, so y is going to be the distance that the top of the ladder is, and I know it's sliding down the wall at a rate of 2 feet per second. So dy, that's the change in y. dt, that's the change in time. Look at the units on this. This is y is in feet, time is in seconds. So I know that it's a negative 2 feet per second. Why negative? The only reason I put negative is because y is getting smaller. So y is getting smaller, it's going in the negative direction. Again, dy dt means the change in y with respect to time. Y is your distance, so that makes sense, it's feet, and t is time. The distance from the top of the ladder to the ground is changing with respect to time. Okay, what else do we know? Well, we know the ladder's 26 feet, but that's kind of given. We'll just keep that in our picture here. What is this saying? At what rate is the bottom of the ladder moving away? So this tells me my want. What do I want? I want the rate at which the bottom of the ladder is moving. That's my dx dt. And then what I put here, when at a specific moment in time, when the bottom of the ladder is 10 feet away, when x is 10 feet. X is not always 10 feet. That's why I don't put a 10 right here. Remember, we're like pulling the bottom of the ladder out, which would be really rude if someone was on the ladder, and it's causing the top to slide down. And X is not always 10. I just want dx dt at the moment when x equals 10. Okay? So I've assigned my letters. Now I need some way to relate my variables together. So the way we're going to do this, because this is always the way we do this when we deal with right triangles and we're living in perfect math world, is I know x squared plus y squared equals 26 squared. And this is going to be what I'm going to use to take the derivative. So let's square 26. That's 676. And I have to have this equation. I need some sort of equation to relate my variables. I need some way to relate my x and y, because what do I want? I want dx dt, so I need to take the derivative of something. So I need something. Anytime you have a right triangle, it's going to be the Pythagorean theorem. Another example might be, you're just given the function. So what I'm going to do now, I'm going to take the derivative of both sides of this function with respect to time, right? Because what I care about is how are they changing with respect to time. Not how is y changing with respect to x. I don't care about that. What I care about is how is this changing with respect to time. So x squared, I'm going to do the general power rule. The derivative of the outside is 2x. How is x changing with respect to time? Well, we'll just say dx dt. What about y squared? That would be 2y times dy dt. That's the way that y is changing with respect to time. And this represents the length of the ladder. Well, the length of the ladder is not changing with respect to time. Now, again, what do we want? We want dx dt, right? So here is dx dt. That means we should be able to find values for the rest of these. So when x is 10 feet, what do I know? When x is 10 feet, right, I need to figure out what y is, okay? And this could also, so I just want to show you that I could actually be putting this under my givens also. I want that x is, at the moment in time when x is 10 feet, that means 10 squared at that moment in time. What is y? Well, let me check. It'll be 24. If you solve this all out, what you get is you get y to be 24 feet. And now, look at what we're able to do then. This 10 right here is going to go into this x right here. This y, the 24 feet, right? I'm looking at this moment in time. We'll go in for this y. And then this -2 is going to go in here for the dy dt. Okay, and then we'll be able to solve for dx dt, which is what we wanted. Yes? Yes, that's what we want. Nope, I do not want a keyboard. All right, so let's plug that in. So if I plug this in, I'm going to get 2 times 10 feet. Okay, dx dt, that's my unknown, plus 2 times y, which is 24 feet, times a -2 feet per second, right? All of that equals 0. So let's simplify a little. So I get 20 feet times dx dt, right? Equals, well, what is this all going to equal over here? Well, I have 4 basically times 24, which is 96. So all of this here is a -96 feet squared per second. So I'm going to add that over to the other side. So if I take this guy, remember this was all equal to 0. I kind of ran out of room. Add that over, I get 96 feet squared per second. And now what's my last step? Oh, I'm sorry, I'm running out of room. I'm going to solve for dx dt. And look at what we get here. We get 96 divided by 20, which isn't going to be a perfect number, and that's okay. A lot of times these won't. This is 4.8. And what happens is when I divide by this, those feet will cancel, and I just get feet per second. And that makes sense, right? And should it be a positive? Yes, because x is getting bigger. This is, the top is sliding down. That means the bottom is going out. I hope that makes sense. And then I would state the answer in a sentence. Of course, we state our answer in a sentence. All right, let's do one more, and then we'll call it good. So I wanted to do one more where you're actually given the function, and this is pretty nice. And I won't, I'm at 20 minutes already, so I'll try and speed this up a little bit. But look at what this says. Suppose the price P in dollars of a quantity of X items is given by this function. So notice it is not super easy to solve for P. I could do it, and I wouldn't be scared of it, but I could solve for P, but it's not super easy. But here, so even if I could solve for P, here's the problem. X and P are changing with respect to time in weeks. I need probably a comma in there. Determine the rate at which x is changing when x equals 4, p equals 3, and the price is decreasing. So what do we want? Wants and givens. What do we want? The rate at which x is changing. That means I want dx dt, right? And when do I want, so here are my givens. So I really want to point out that this is at a moment in time when x equals 4, right? That's the number of items. P equals 3, that's the price in dollars. And look at what this says. The price is decreasing at a rate of $2 per week. So the rate, that means my price is changing with respect to time. Anytime you see a rate, that means you're using a derivative. Negative $2, right, per week. Okay? So we want dx dt. We need an equation that relates these guys together. Lucky us. This is actually given to us. So in this case, I don't even have to worry about finding that equation myself. I'm going to derive, just for time's sake, I'm not going to write that I'm going to derive with respect to t. I'm just going to go ahead and do that. So that would be 6 times dp dt plus, what's the derivative of x with respect to time? That would just be dx dt, and then careful here, people, these are two separate functions of time. So I need to leave the first, take the derivative of the second, plus leave the second, times the derivative of the first. Good. And all of this equals 50. Okay? So again, what do I want to find? I want to find dx dt. So these are my unknowns, but lucky for us, we have a lot of knowns. So I know x is 4, p is 3, and dp dt at this moment in time is a negative 2. So I'm going to just start plugging in. Let's do this. So I would get 6 times a negative 2 plus, I'm going to not worry about my units for right now, which my colleague Steve Shutton, who is a physics teacher, gets really, really mad at me when I do that. But I'm a pure mathematician. So 4 times, what's dp dt again? Negative 2. What is p? That is 3. dx, oh, people, I bet you're yelling at the computer right now. This is 0. What is that? How does that 50 change with respect to time? It does not. That's the thing. It does not change with respect to time. It's constant. It does not care what time is doing. It's constant. All right, and then the dx dt here. And I can think about, I should know what my units are, right? I'm looking at, well, how is x changing? Well, what is x? X is the number of items, so it would be items per week. And if we solve this, this is a negative 12 minus 8. That'd be a negative 20. If I combine like terms, I get 8 dx dt equals 20. If I move that over, 20 divided by 8 is 2.5. So look at what my answer is. My answer, dx dt, is 2.5. And what is x? Items. What is my time per week? I hope that makes sense. These can be tricky, so please don't hesitate to contact me if you have any questions, especially about the related rates problems. If you have questions on them, holler at me and I'll make a video and I'll share that with the whole class if you get stuck on these.